Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the question and answer window. Questions will only be visible to myself and our speaker. So thank you for joining us today. It's now my pleasure to introduce our speaker, Lisa Krapf from Unchained LIBS.
Thanks, Leah, for this nice introduction. Today we're going to illustrate how having the right tool for particle characterization helps. These two candies look very similar from far away. You can usually distinguish the two if you look closely, but anyone who has had both knows that they taste very different. While the M&Ms on the left are filled with chocolate, the Skittles on the right are fruit-flavored chewy candy. Particle analysis is ubiquitous throughout drug product development to manufacturing. Early on in development, characterization such as morphology and size distribution examine crystalline forms or API quantity produced. These properties are important indicators for candidate selection because they can impact bioavailability, performance, and stability. And in later stage, particle identification can be used to inform about product purity and monitor particle changes in formulation mixtures. This information can help fast-track process development, monitor process variability, and to QC the batches before release. There are many forms and reasons to analyze and characterize particles throughout biologics development. For example, it is important to characterize aggregated protein particles to understand mechanisms for formulation stability. Also, API particle size and shape changes during process development can impact bioavailability or inform about process variation. Another example is inspecting raw materials to investigate how their quality impacts the quality and safety of the finished product. And these are just a few examples on why people study particles in biologics development. With different types of particles and different reasons to analyze them, the technique requirements to assess the particles is high. To thoroughly examine the particle, we need to have the ability to describe the particle by count, size, and shape. But particle quantity and morphology does not tell a full story, especially if the particles are in mixed populations. Because of this, identification of particles is also an important consideration for particle analysis. To get statistically significant data to draw the right conclusions, it is also essential to be able to inspect large number of particles in an experiment. The technique should also be easy to use and have minimum impact to particles during sample preparation to prevent introducing unnecessary stress, which can cause further particle size or shape change. This is Hound, the one instrument to cover every particle analysis need of the drug product life cycle. It is the only particle analyzing instrument that can characterize particles by count, size, and shape, while it is also able to perform chemical and elemental identification on the same platform. Hound is also 21 CFR Part 11 compliant, making it a fitting instrument for regulated labs as well. The particle size distribution is a critical quality attribute throughout the life of a drug product. It is important to report the particle size distribution since it directly impacts product safety and drug absorption. Later in this talk, we will show you how Hound can be used to easily and quickly report the particle size distribution. Hound is a fully automated microscope that will automatically acquire images and analyze it for you. It does count, shape, and size distribution for a wide variety of sample types, whether the particles are in solution or dry dispersed. Hound can automatically scan and stitch a large view area when it images a sample. It detects the particles on each image, counts the particles, and stores size and shape information for each particle. It also tracks the coordinates of the particles so that you can go back to find the particles of interest at any time to do further analysis. Hound can analyze particles in a size range from 2 micrometers to 15 millimeters. Hound's user-friendly software lets you set up custom size bins so you can focus on particle sizes that are important to you. In this specific example, only particles larger than 10 micrometers were of interest, so the lower limit was set to 10 micrometers and the size bins according to the application. Sample preparation for Hound analysis is very straightforward. If you have particles in solution, you can filter the particles on a gold-coated membrane filter and directly analyze the immobilized particles on the filter round. If you have powdered sample, you can directly disperse the particles on the filter round and analyze them right away. Let's have a look at a first example where Hound was used for particle counting. It is important to analyze foreign particles from an inhaler device for assessment of device safety, but collecting all the particles generated from an inhaler spray can be cumbersome. In this example here, we will demonstrate an innovative way we capture particles from an actuated inhaler and easily analyze the insoluble foreign particles on Hound. 2 actuations of a metered dose inhaler were collected in a particle-free and airtight collection device that you can see on the second picture from the left. To be able to quantify foreign particles, the API and excipient particles of the 2 doses need to be removed. To dissolve them, 70 milliliters of solvent was added. The liquid was then filtered using our 0.8 micrometer filter round to isolate the insoluble particles on the filter. The particles are then set to dry out and directly mounted on Hound for automated count and sizing. And Hound is fast in counting. It can generate a complete size distribution report of more than 6,000 particles in 2 minutes with automated counting and sizing analysis. In our inhaler example here, Hound's counting capability was used to evaluate foreign particle load of 2 different types of inhalers by looking at particles of 2 micrometer and larger, resulting in the size distributions you can see on this slide. The need to characterize particle size distributions will never go away in the drug product life cycle, but it will become increasingly challenging to get the correct particle size distribution in the later development stages as the composition of formulation becomes more complicated than just a single active ingredient. Particle identification techniques become important to help isolate the particle population of interest among the fillers or excipients. In the later presentation, we will show you how Hound can solve the issue of particle characterization with complex mixtures by combining its image analysis capability with chemical and elemental identification. Besides providing particle characterization, such as counting and sizing, Hound can also perform chemical and elemental ID with Raman and laser-induced breakdown spectroscopy, which I will mostly call LIBS during the rest of this presentation. It has 3 laser options to ID almost anything. The 3 lasers are Raman 785 and 532 nanometers and laser-induced breakdown spectroscopy. The dual Raman lasers in Hound can perform chemical fingerprint on a wide range of particles. The red 785 nanometer laser can help to ID fibers and contaminants such as lab wipes, while the green 532 nanometer laser is ideal for identifying protein aggregates. Both lasers can identify particles down to 2 micrometers and use a built-in and customizable reference database to compare the collected spectra and find a match for the material of the particle. Raman can identify a wide range of organic and inorganic materials, again down to 2 micrometers, based on their chemical structure. It can identify cellulose, protein, different polymers, or even the polymorphs of a compound. Unlike FTIR, Raman is inert to water, so identifying biologics or particles in solution is not a problem for Raman. Hound uses gold-coated filter rounds as the gold surface is Raman inactive, which results in low noise and high-quality spectra. Hound uses LIBS to identify metal and other organic particles down to as small as 20 microns. For laser-induced breakdown spectroscopy, a high-energy pulsed laser is focused on the surface of the particle, ablates a small volume of the particle, and creates a plasma. When the atoms in that plasma fall back to their ground state, they emit element-specific spectra that are measured for material identification. Like Raman spectroscopy, LIBS identifies the particle material by matching unknown spectra to built-in or custom-added spectra in a reference database. It is a great addition to Raman spectroscopy, which is not sensitive in picking up glass or metal signals, while these materials typically provide a great and very material-specific signal when doing LIBS. The other great thing about LIBS is that it only needs 1 second to identify a particle. For LIBS, no additional sample preparation is required. It is very sensitive and can distinguish minor variations in material, like discrimination of steel particles or glass fragments from different sources by their elemental composition. Lastly, as LIBS ablates a small volume of material on the particle surface, it can also be used to perform a layer analysis by taking several measurements on the same position and observing the changes in elemental composition while acquiring spectra from different depths. Besides using the gold-coated filter rounds to filter out solutions or disperse dry powder samples on the round, users can also directly apply samples in different formats, such as gel or slurry on the gold-coated wet round without additional dilution or preparation. And if you want to study particles in solution, simply load the colloidal or biologics in solution on wet rounds to analyze the sample in situ without worrying about introducing additional sample shearing or breakage during sample preparation process by filtration. In this next case study, we will take a look at the API distributions in a topical cream without additional sample preparation using the wet round. In this topical cream example, it is very challenging to separate two similarly sized and shaped APIs with just count, size, and shape characterization alone. We will show that we can use Hound's Raman spectroscopy capability to obtain the particle size distributions of the two different APIs in a mixed sample. This helps to understand the composition of the topical cream formulation and can, for example, be used to compare batch-to-batch variation. Using a Raman inactive gold-coated wet round, the topical cream can be directly smeared on the slide and analyzed on Hound without any additional sample suspension or dissolving steps. As you can see from the image captured by Hound here, The API particles in this topical cream are similar in size and shape. It will be impossible to distinguish the API populations by just size, count, and morphology alone, which a traditional microscope would be able to do. Knowing the APIs are adapalene and benzoyl peroxide, we created a custom reference spectra for both APIs and then used Raman spectroscopy on Hound to analyze enough particles to get statistically meaningful size distributions for both APIs. Using fully automated Raman analysis mode, Hound can identify and distinguish over 4,000 API particles in less than 3 hours. Using Raman spectroscopy combined with image analysis for size distribution, we can get distinct API size distributions from the 2 different APIs of similar size and shape in this mixed sample. In this topical cream, about 3 times more benzoyl peroxide particles were found than adapalene particles, as can be seen in the table on this slide. We also get information about the size distribution of each particle type. For example, benzoyl peroxide has a D90 value of 23.7 micrometers, while the D90 value of adapalene is only 7.6 micrometers. Using the automated Raman spectroscopy feature on Hound, precise API characterization, including count, size, and chemical identification of the topical cream, was done quickly. It is a perfect tool to quickly give answers to minor changes in particles to fast-track formulation and process development. Hound image analysis also performs morphology measurements such as rectangularity, elongation, equivalent circle diameter, and fibrosity for particle classification. The morphology grouping in combination with identification makes Hound an efficient and rapid identification tool, which we will also show in the next example. In this nasal spray evaluation example, we would like to assess the size distribution of 1,000 API particles that are mixed with high filler content to ensure product integrity. The challenge is that the API content ratio is so low in this nasal spray formulation that looking for 1,000 API particles would be like looking for the needle in a haystack. In this example, an initial analysis determined that the relative number of API particles in the sample was 2%, while the cellulose filler content was 98%. From this, we learned that the elongation factor of API particles was always below 2.5, in contrast to the cellulose particles that were typically slightly elongated and had an aspect ratio of up to 5. A secondary selective analysis method was then set up to automatically direct Raman identification towards particles with elongation factors less than 2.5. This morphologically directed Raman analysis increased API particle detection rate from 2% to 34%. As a result, only 3,000 particles need to be identified to achieve 1,000 API identifications, as opposed to 45,000 particles needed without morphology classification beforehand. With the morphology classification to home in the API population, identification of 1,000 API particles was achieved 15 times faster. In this nasal spray example, the average API size is 5.2 micrometers with a D90 value of 12.5 micrometers, as we can see from the graph. By adjusting particle selection parameters to perform image-directed identification, it was possible to just focus on particles of interest without wasting time screening through all particles in a sample. This makes Hound great for precise characterization of particles of interest in complex mixtures. Another application of Hound is the characterization of contaminants. One major reason for batch failures, for example in injectables, is when visible particles are found in the product. Those particles can come from a variety of sources, including materials that are intrinsic to the product, like protein aggregates, or they can be external contaminations from any step in the manufacturing process. When these contaminations occur, you usually want to find out how critical they are, where they come from, and hopefully eliminate the root cause of the particle contamination. Hound can help you by quantifying the particle contamination and even identify the root cause using Raman and LIBS to figure out particle material and compare it to your lab or production-specific possible particle sources. In the example we show here, fibers were found in a product and it caused 3 batches of the product to fail. Therefore, there was an urgent need to find out where those fibers come from and eliminate the source of the particles. On the slide, we see a picture of one of these fibers and a Raman spectrum that clearly shows that it's a cellulose fiber. But in addition to knowing that it's cellulose, we want to know which is the particular cellulose source of this fiber. Luckily, the Raman spectrum shows an additional peak at 1600 wave numbers that is not present in most cellulose spectra. So we can use this peak to find the specific source of the contaminant. An investigation was started to find out where in the process those fibers appear. First, lab equipment and supplies were rinsed and the wash liquid was filtered to find out where the fibers appear. On the slide, we see examples of 3 of the samples that were taken. First, the rubber stoppers used in vial capping were analyzed, then they rinsed the clean-in-place equipment and the tubing that was used in the process. The filters prepared from those rinses were analyzed on Hound, and some fibers were actually found, as you can see on the pictures. But when taking Raman spectra of these, it turned out that none of these fibers had the characteristic peak at 1600 wave numbers that was seen for the contaminant. So the next step that was taken was to collect all types of cellulose materials in the lab, take spectra of those, and compare them with the contaminant spectrum. On the slide, you can see the range of materials that were collected, including different clothing fibers, lab wipes, and fibers of autoclave bags. The graph shows spectra of all these materials, but as you can see, none of them has the extra peak at 1600 wave numbers. And also the overall matching ranks between the contaminant spectrum and these spectra are poor. So there was a hint that none of these is the actual contamination. So another step was taken and possible contamination sources were investigated upstream in API manufacturing. Again, several samples were taken from different cellulose materials and reference spectra acquired. And this time it turns out that there is actually one material giving a spectrum that has the very specific peak at 1600 wave numbers. Unfortunately, the yellow graph in this picture. But that one actually matches very well with the contamination fiber spectrum. So it became clear that this was probably the source of contamination, and the spectrum belongs to a cellulose lab wipe. So now there was a very good hint about what was the source of the contamination, but it wasn't clear yet how it got into the product. To figure out that last question, the tanks that were used in manufacturing were rinsed and the rinse filtered and analyzed with Hound. The picture on the right that was taken with Hound shows the fibers that were actually found in the tank. Spectra were taken of these fibers, and in fact, they also matched the contamination fiber and the sample taken from the lab wipe. With this information, they could figure out the pathway how particles got into the product. The tanks were cleaned with lab wipes that released fibers, and those fibers finally ended up in the product. Knowing this pathway, the particle source could be easily removed. Another example showing how metal contaminants such as stainless steel or crimp cap shards can also be identified with Hound is shown on the next slide. Hound can also be used for root cause investigation for metal contaminants using laser-induced breakdown spectroscopy. In this example here, Hound could identify a particle originating from a crimp cap as aluminum. However, knowing the material is aluminum can be too broad to understand where the shard actually comes from. So why stop at knowing the contaminant is an aluminum shard? By creating a complete custom reference spectra library, precise matching can be achieved to know the exact root cause of where the particle comes from. In this example, a precise match down to a name brand of crimp cap can be achieved by adding a custom crimp cap reference spectrum like this Wheaton crimp cap. LIBS is sensitive enough to catch the subtle difference in the 403 nanometer peak to ID the contaminant culprit is not just an aluminum shard, but an aluminum crimp cap. This illustrates the power of the customizable reference library that can give you a specific contaminant source. Hound comes with over 150 Raman reference spectra and 50 LIBS references. To get exact matches for the unique particle of your interest, you can add a reference spectrum of materials specific to your process into the reference database for future matching. It takes only 15 minutes to load the samples, obtain a spectrum from the material of your interest, and add it to your custom reference database. The more specific references you add to the database, the more precise the match will be. Hound can be used for a variety of applications that need particle characterization and identification. It can provide quality and quantity information of the drug product through particle characterization, and it is the only particle analyzer equipped with Raman and LIBS identification capability to properly monitor process variability and batch release. Hound is a microscopy-based particle analysis tool that can provide quick automated or manual particle count, size, and detailed morphology information with large scan view area in just minutes. It is easy to prepare sample and retain sample integrity since it can take samples in wet or dry format. It can also rapidly identify particles and mixtures by using image-directed particle Raman or LIBS identification. Hound is made for regulated lab environment with its 21 CFR Part 11 compliant tool. In summary, I hope Hound will help you when you find yourself in a situation where you cannot easily distinguish particles of the same size and similar shape, and you need another technique besides just size to distinguish between the two. Thanks for listening. I'm happy to answer any questions now.
Okay, great. Thanks, Lisa. So the first question is, are there ways to do particle analysis for a combination device?
Yes, so depending on the device, that can look very different. One example could be that you can just spray the contents of the device directly onto a surface or extract them with a solvent and then put that substrate on Hound and analyze away. In some cases, people even put the whole device under the microscope and analyze particles directly on the device, which can have benefits because if you do a preparation step, there might be a risk to get lose the particles. So yeah, there are different options to do that, and yes, it's possible.
Okay. If I filter a whole sample, can I only count and report visible particles?
Yeah, that's totally up to the user. So the size range of particles that Hound will count can be set up, and you can only focus on visible particles if you want that, or you can count the whole range from 2 microns on. And you can also define the size bins that particles are grouped into, depending on the requirements you have for your application.
Okay. If the particle looks non-uniform, can I identify it at multiple locations?
Yes, that's also possible. So Hound has a what we call manual mode, where you can basically just point at whatever location you want to analyze. And if you use that manual mode, you can analyze as many positions on a particle as you want, using both the Raman and the LIBS laser.
And for the contamination example, can I export data and transfer to multiple production sites?
Yes, that's also possible. So what you do in that example basically is you we saw that those guys have identified a lot of different possible contamination sources, like the different clothes or fibers from bags and tissues. What they did is they made spectra of those, added those spectra to a database, and those databases can be exported from a system and then just imported on a different system and used on multiple sites that way.
Okay, and as a reminder to the audience, you can just go ahead and type in your questions. So for the contamination example, oh, I did that one. Okay, we do particle ID by FTIR. Are there advantages to ID by Raman?
Yes, there are some advantages of Raman over FTIR. One of them is that Raman doesn't interfere with water. So if you do FTIR on aqueous samples, you will only see water signal, and that's why it wouldn't be possible to do what we can do in our wet round, where you can put an aqueous sample and then just identify the particles in the liquid. Another benefit of Raman in comparison to FTIR is that we can go to lower particle sizes. So FTIR usually stops at about 10 to 20 micrometers. With Raman, we can measure particles of sizes down to 2 micrometers.
Okay. And can it handle polymorphs with different morphologies as well?
Yes, that's another application Hound is being used for. So an example that comes to my mind, we analyzed as a mixture of polymorphs, and the composition is unknown, and you want to find out the size distribution of each polymorph in that mixture. The way you would do that is have a reference substance for each polymorph, so that you know the spectra of each polymorph, add that to a database, and then you can do an automated measurement similar to the one we saw for the cream example, where you analyze lots of particles, and get a size distribution for each polymorph. And in addition to that, you also get the morphology parameters of each particle you analyze. And similar to the nasal spray examples, you could also use that morphology in the same way to specify which particles you want to analyze. For example, if you're only interested in a certain subset of particles in the mixture, like the more elongated ones or the more fibrous ones or whatever. So yeah, that's a very common application too.
Okay. And are the particle images good quality? Are there options for lighting the particles differently?
Yes, so we use a 5 megapixel camera on Hound that provides very good pictures. And we actually have also different imaging options. So we mostly use dark field imaging for counting the particles because it gives us the best contrast and also better than bright field imaging. But bright field imaging is also available and can be used, and we can also use different filter types if that's required for the application. And then a third thing that's available in Hound is polarizing filters that can be used to get that additional contrast information when looking at polarization.
Okay. Well, I think we are going to just go with one more question. If we didn't get to your question today, we are going to pass those on to Lisa, and she can follow up with you directly. So the last one is, how thick or dense can a sample powder be before you're unable to detect the particles correctly?
In principle, yeah, what you want to do if you want to really accurately size particles, the single particles should be separated from each other in the ideal case. So because if they lie on top of each other, the instrument wouldn't be able to see that it's several particles in comparison to one big clump or aggregate. So for sizing, this is important. If you just want to generate spectra, it actually doesn't matter. You can just point to whatever position on the sample and take a spectra and get the material information. Might be a pure material or a mixed material when you have a very clumpy and mixed sample. Again, if you want to get the sizing information, there should be a reasonable load of particles on your substrate to be able to see single particles instead of aggregates or clumps or a whole layer of particles.
Okay, great. Thanks, Lisa.
Thank you.
And thank you to our audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.
Goodbye.